In this video, we'll talk about an introduction to parametric equations. So to start this off, let's look at an equation that gives us a graph of a circle. So specifically, let's look at x squared plus y squared equals 9. Like I mentioned, the graph is a circle. We can see that here. Does not pass the vertical line test, so y here is not a function of x. Also notice that it doesn't pass the horizontal line test either, so x is not a function of y. So no matter which way I try to do this, y being a function of x or x being a function of y, we'd have to break it into two pieces. Okay? So let's see if there's another way we can possibly write this. Well, let's say we consider the central angle theta, which I'll draw another picture here in a second, where we have the positive x-axis as an initial side. Here's the center of the circle, so we have a theta where the terminal side here is coming out as a ray from the origin. Then notice that we can express both x and y as functions of theta. So here's the picture. Here's positive x-axis as your initial side. Here's terminal side, making our theta. You can check that the x-coordinate here is certainly 3 cosine theta, because this is a radius of 3. So this side would have length 3 cosine theta. And then the y-coordinate would be 3 sine theta. Okay, so notice that here we have x and y, both functions of another variable, theta. So when we write a curve where our x and y coordinates are given in terms of functions of a specific third variable, we usually call it t, we say these are parametric equations for the curve, and the variable t is referred to as the parameter. All right, so let's look at another example here. Let's say we have the parametric equations x equals 2 minus 3t and y equals negative 1 plus t. This one asks us to sketch the curve represented by these parametric equations. So in this case, we're given parametric equations. We're going to sketch the curve, and that's going to be usually the way that we're interested in it. We're going to be given a set of parametric equations and then asked to do some sort of calculus things on it. You could also go the other way around. You could also be given a set of points and then determine what the parametric equations are. Do a little bit of that, but mostly we're concerned with we have a set of parametric equations. What can we do with them? All right. So thinking about what you probably did when you first started learning how to graph equations, you picked some values for one of the variables and then got values for the other variable. So usually you were picking values for x and get out values of y. It's typically how you first do it. In this case, though, remember that both of these x and y are in terms of a function t. So what we're going to do is we're going to pick some values for t and get out values for x and y, and then plot the ordered pair x comma y. So let's just make a table. That's one of the first things that you do when you try to graph an equation. So again, we're going to pick some values for t. Doesn't matter what they are, as long as they are in the domain of both functions. So I'll just try, say, between negative 3 and positive 3 and see if we can get an idea of what the graph has to look like. So if t is negative 3, if I put negative 3 in for t for x, I get 11. When I put negative 3 in for t for y, I get negative 4. So now just pick another value for t, say negative 2. Put that in for x and y, you'll get 8 and negative 3. And then again, just go on up the line. Like I said, pick some values for t and get out values for x and y. Now, we won't explicitly put in these values for t on the graph. There will be an implicit way to do that, and I'll talk about that as we go forward. But the points that we're going to be interested in are the x, y coordinates here. What's the x coordinate? What's the y coordinate? Plot that point. So we would plot the point 11, negative 4. We would plot the point 8, negative 3, and so on up the line. Okay? So we're going to plot those points and sketch what the curve has to look like. So let's do that. In this case, we'll get a line. So this looks like. And we'll have a way that we can verify that this is a line, but if we just plot those points and just connect the dots like you would do any other time, we'll get something that looks like a line. We can also, I didn't do it on this particular curve, and this is where I said we could put t implicitly on the graph but not explicitly on the graph. We can also indicate the direction that the curve is traced out in as t gets bigger. So going back to what the equations were, notice that as t gets bigger, the x value gets smaller, goes in the negative direction, and as t gets bigger, the y value gets bigger. You can see that here in the graph, right? T gets bigger, x's get smaller, y's get bigger. So if we were going to put arrows on here, we would draw the arrows this way, put arrows this way on the graph, because as t gets bigger, the x's are getting smaller and the y's are getting bigger. So it would be getting traced out in kind of this backward direction. When we put the arrows on there, we would typically refer to that as a plane curve. All right. So I said a minute ago that we could also verify that we really did get a graph of a line here. In particular, that the parametric equations that we have really do represent a line. So we can do that in this case by doing what's referred to as eliminating the parameter, meaning that we can write a single equation, y in terms of x in terms of y, or just relating x and y, that doesn't have t in it at all. So one typical way to do that is just to take one of the equations and solve for t. So here if we solve the x equation and solve it for t, we get t equals 2 minus x all over 3. Plug that in to the y equation, and we can simplify that, and so we'll get the equation y equals negative 1/3 x minus 1/3. We really do see now the equation of a line. This is actually in slope-intercept form. The intercept is negative 1/3 for the y, so we see that on the graph there. The slope is negative 1/3, and we can see that as well, since we got a downward to the right sloping line. And notice again here, now we've got y in terms of x, no t's. That's eliminated the parameter. See if we can do another one like that. So let's say we have the equations x equals e to the t, y equals e to the 2t plus 1. This should say eliminate the parameter. That's a nice typo there. Eliminate. All right. So in this case, well, the previous one we solved for t in terms of one of them and just plugged it in the other. In this one, though, we can be a little bit more clever. We don't actually have to solve for t explicitly. So let's start with the y equation. Notice here I've got 2 times t in my exponent. So I can rewrite that as e to the t quantity squared. And now I notice that x is equal to e to the t, so I can just replace all of that e to the t with x and get y equals x squared plus 1. So this is an equation of a parabola. However, we have to be careful when these are in terms of a set of parametric equations. The careful is that notice that our x here is defined as e to the t, meaning that x can never be negative. It also cannot be 0, right? E to the t is always positive. No matter what I plug in for t, e to the t is always positive. So we'll never get this left-hand side of the parabola. So the x always has to be greater than 0. We'll get the right-hand side. And so really the graph is only this right-hand part. Okay? If we wanted to get the plane curve, putting the arrows on the curve to indicate how the graph is being drawn as t increases, well, as t increases, e to the t increases. E to the t is an increasing function. So that means our x gets bigger and bigger. So we would draw our arrows pointing to the right because we would trace it out in this fashion. X is getting bigger. You can make the same kind of analysis with the y getting bigger as well.